The goals for this chapter, for these lectures are the following. The first one is define the electric field. The second one, learn the distinction between electric force and electric field. Third point, calculate the electric field due to a discrete charge distribution. The last point is study the motion of point charge in uniform electric field. That's nice. So before we start, and as usual, I'm always making a review about the last lecture. In the last lecture, we talked about Coulomb's law. And we said that according to Coulomb's law, what do we have? If there is a force between 2 points of charge, whatever they are, positive, negative, same sign, different sign. If we take an example, the 2 point charges are positive. So the force exerted by 2 on 1, and this is the force exerted by 1 on 2. The magnitude of the force exerted by 2 on 1 is equal to the magnitude of the force exerted by 2 on 1. According to Coulomb's law, it's equal to K, Q1, Q2 divided by R squared. So we can say that it's equal to K multiplied by the product, the absolute value of the product between the two charges divided by the distance between them squared. And we know that K is equal 9 times 10 power 9 Newton meter squared per Coulomb. Okay, per Coulomb squared. Per Coulomb squared. Okay, so it's clear this is the distance between the two charges. The distance R between 1 and 2. And then we talked about the superposition principle, and we said according to the superposition principle, if we have a point of charge 1, a point of charge 2, both of them are positive, whatever the sign, and we have a negative charge, for example, 3 here. We want to calculate the force exerted by the two charges on the charge 3. So on the charge 3, there is an attraction between 1 and 3. Let's say this is F1 on 3, and this is F2 on 3. Both of them are attractive, so because they have different sign. According to the superposition principle, the vector of the force applied on the charge 3 is the vector sum. We draw the parallelogram formed by these two vectors, and this is our vector F3. Regardless the sign of the charge, regardless the amount of charge, so it's the vector sum is F1 on 3 plus F2 on 3. And we said if our vectors have two components, so we must write this equation along x and the same along y. And then our vector F3 is F3 along x component plus its y component, F3 y. Good. So this is a short review about what we saw in the last time. Today we will start talking about the electric field. A source charged body Q produces an electric field in the space around it. So if we have a point of charge, we have an electric field. We use a small test charge Q naught to find out if an electric field is present or not. If we take, for example, let me explain here, and let me make a summary without going deep in the details. If we have a point charge, whatever it's positive or negative, Q, this point charge produces an electric field. And since the charge is positive, so the electric field is outward. Outward. The electric field is outward in all the directions. Okay. Now imagine that we have In negative charge, the electric field is inward. Okay, it's inward. Inward. It's inward. Okay, good. So to figure out the presence of the electric field, we take a positive charge Q, and there is a test charge Q naught. According to Coulomb's law, there is a force between these two charges. This force is a repulsive, equal FQ on Q naught. Good. That's very nice. Okay. Now, according to the definition, FQ over Q naught is equal to what? Equal to Q naught multiplied by the vector electric field E. Okay, so this is the electric field E. So as a definition, our electric field is equal F over Q naught. Very good. So this is our electric field. As a definition, the electric field E is equal K Q, not Q naught, it's Q, the charge responsible for the production of the electric field, divided by the distance from the charge to the point. Let's say this is our point P, where the Q naught is located. Square it, multiplied by a unit vector. It's okay? So this vector is called unit vector. According to the definition, the unit vector is equal to the vector R divided by its magnitude. And the magnitude of R itself, of the unit vector, is 1, as it name states. What is the vector R? This is our vector R. The vector R from the charge to this is our vector. What is the unit vector R? R hat. This is our unit vector R. It's the magnitude of the vector divided by its magnitude. I would like to say here that the vector R hat is unit vector pointing from the charge Q to the point P, where we want to calculate the electric field. It's okay? This is very, very important. So the unit vector R is pointing from the charge Q, responsible for the protection of the electric field, to the point P, where we want to calculate the electric field. And as we said here, it's from the charge Q to the point P. Good. Let's continue. And of course, as you know, K, it's the same like the previous lecture, times 10 power 9 Newton meter squared per Coulomb squared. The electric field E, we said, which is equal KQ over R squared multiplied by the vector R hat. Its unit is Newton per Coulomb, because we said it's a force divided by a charge. Did we take the absolute value of Q? No, we don't take the absolute value of Q. We don't take the absolute. It's okay. So this is short summary about what we're gonna learn today. Good. If the source distribution is a point charge Q, it is easy to find the electric field that it produces. We call the location of the charge the source point, and we call the point where we are determining the electric field point. So this point is called, if we have, for example, positive charge Q, and we have a point P, this point is called source point. And this point is called field point. What is the vector R? The vector R hat, the unit vector of the electric field. This is, oh, sorry, R hat. What is the vector electric field? Uh, this is R hat, from the charge to the point. What is our electric field? This is our electric outward, because the charge is positive. Good. Let's continue. It's also useful to introduce a unit vector that points along the line from the source point to the field point. Good. Now, if we take negative sign, negative charge Q, and we want to compute or to calculate the electric field at this point, what is the direction of the electric field? What is the electric field? The electric field is inward. Why? Because the charge is negative. And what is the unit vector? The unit vector always from the charge to the point, always pointing from the charge to the point, okay? Whatever the electric field is inward or outward, regardless the sign. Okay, the electric field E at a point in space is defined as the electric force F acting on a positive charge placed at that point divided by the magnitude of the test charge Q naught. Very good. So, and this is the definition of the electric field as we see. Let's continue. According to the sign of Q, Q can be positive. The electric field E points radially outward from Q. If the point of charge Q is negative, in this case, the electric field is inward. As we see. It can vary from point to point. It's not a single vector quantity, but rather an infinity set of vector quantity, one associated with each point in space. This is when we have positive charge. It's outward in all the directions. Okay, the field E strength decreases with increases the distance. So if we go far from the point, the electric field is decreasing. Why? Because it's proportional to 1 over r squared. We take a quick example. A charge of 3q is at the point P where the electric field is directed to the right and has a magnitude of 4 times 10 power 6 Newton per coulomb. If the charge is replaced with the -3 microcoulomb, what happens to the electric field at the point P? Okay. The first situation A, the charge is 3 microcoulomb, and we take this is our electric field, our point. The electric field, he said, it's outward directed to the right. So this is E1. In the second case, we will substitute this charge by a negative charge, but the same magnitude, -3 microcoulomb. And we want to calculate the electric field at the same point P. How is it the electric field? It's inward, because the charge is negative. Now, let's talk about the magnitude of these two fields. It's K, Q1 over, okay, let's talk about the magnitude. In magnitude, E equal E1 equal K, Q over R squared. The unit vector, خلاص, it's gone, because the magnitude of R hat is 1 in magnitude. Okay, for the second vector, it's also, let's say this is Q1, and let's say this is Q2. It's K, absolute value of Q2 over R squared. We changed only the amount of charge Q1 and Q2, but Q1 in absolute value is equal to Q2. So the magnitude of E1 equal to the magnitude of E2, but opposite direction. Opposite direction, but same magnitude. So this is what happened when we substitute the charge 3 microcoulomb by minus 3 microcoulomb. Let's continue. So there is a similarity between the electric force and the gravitational force. For the gravitational force, Fg equal minus G m over r square. The field is equal minus G m over r squared multiplied by unit vector. For the electric force, for the electric field, we have kq over r squared multiplied by r hat. It's nearly the same form. And for that, the gravitational force is m multiplied by g, and the electric force is q multiplied by e. Okay, good. Let's take this example. A point charge q equal minus 8 nanocoulomb is located at the origin. Find the electric field vector at the field point x equal 1.2 meter and y equal minus 1.6 meter. So we have a point of charge negative. The electric field is inward. Okay, the electric field is inward. As usual, I would like to draw the situation by myself to explain better. Good. So what do we have? We have a negative charge at the origin, negative charge. Okay, this is the positive y, and this is the positive x. Where is our point? Our point is located at the coordinates 1.2 along x. So this is, let's say this is 1.2. And negative 1.6 along y. And this is negative 1.6 along y. So our point is here. This is the point P. Okay? So we want to calculate the electric field produced by the charge Q at the point P. Since it's the charge is negative, so the electric field is inward. This is the electric field at the point P. We want to draw the unit vector. The unit vector, as we said, it's always from the charge to the point, regardless the sign of the charge. So this is r hat. Okay, good. That's very nice. What is the distance r? The distance r is said in the figure 2 centimeters, which is equal square root of 1.2 squared plus minus 1.6 squared, because we have right angle triangle. Okay, that's nice. So the distance r is the question now. What is the electric field? E, as we said, according to the definition, it's k u over r squared multiplied by unit vector. So we have some steps to follow. The first step is to figure out this quantity. The second step is to figure out the unit vector. Let's start by the first step. K q over r squared is equal 9 times 10 power 9 times what is it? What is minus 8 nanocoulomb? Minus 8 times 10 power negative 9. Should we put an absolute value? No. Divided by the distance between them, so it's 0.02 squared. What about the second quantity? The unit vector r, we said it's the vector r divided by its magnitude. What is the vector r? The vector r points from, what is it? Okay, we take it. The vector r extends from the charge to the point. This is our vector r. So the vector r has 1.2 along x, 1.2i, and along y, minus 1.6. Good. Along j. Divided by its magnitude, the magnitude of this vector is 0.02 something. Okay, let's write it's 1.2 meter and to, oh no, oh, sorry, we said it's meter here, not centimeter. It's meter. And we did a mistake, sorry. And it's 2 meter. 2 meter, yes. And here also not 0.2, it's 2 meter. Very good. So as it's written here, 2 meter, not 1.2. Very good. Okay. So what will be 1.2 over 2? It's 0.6i minus 1.6 is over 2. It's 0.8j. Very good. And of course, the unit is a meter. So this is our vector r. Let's try to calculate this quantity. We said it's 9 times 10 power 9 multiplied by k by q. Q is minus 8 times 10 power nanocoulomb. That means negative 9, good, divided by the distance squared, so 2 squared. It's 2 meters. So what will be the result? The result is a negative 18. Negative 18. So it's negative 18. Newton per Coulomb, of course. Now we want to figure out the vector itself. What do we say as definition? We said E equal KQ over R squared multiplied by unit vector R. The first quantity is what? The first quantity, we said it's negative 18, right? Negative 18. Multiplied by the unit vector, it's 0.6i minus 0.8j. Very good. And like that, we can get the result. The vector E is 18 multiplied by 0.6 is 10.8 I minus 18 multiplied by 0.8 will be 14.4 J, and this is our vector. Don't forget that the unit is Newton per Coulomb because we are talking about electric field. Good. Any question, please? If we go through the magnitude and the direction, the magnitude, of course, E equal square root of 10.8 squared plus 14.4 squared. We can cancel directly this negative sign. No need to write it because it's squared. So it's a square root of 10.8 squared plus 14.4 plus 14.4 squared. Good. So this is our result. Our result is 18. The magnitude of this electric field is 18 Newton per Coulomb. What about the direction of this electric field? Let's say the angle is theta. Theta is tan inverse of EY over EX, which is equal tan inverse of EY how much? Minus 14.4 divided by 10.8. So it's a tan inverse minus 14.4 divided by 10.8. And we close the bracket to get the result. So our result is negative 53.1. So it's negative 53.1 degrees. Our vector, in which quadrant is it? Our vector is in the second quadrant. This is X, and this is Y, and this is our vector E. What is minus 53.1? So this is negative 53.1. So to get our results starting from the positive x, so it's this is our theta. Theta should be 180 minus 53.1, which is equal 180 minus 53.1. So the result is 126.9, 126.9 degrees. Good. So we are done with this example. Let's move to another one. Any question, please? Did you have any question? No questions. I think that there is something missing. Something is missing. Oh, we missed this negative sign here and negative sign here. Yeah, because we have minus 18, not 18. Good. So it's almost the same results because we got the same, but the electric field should be negative 10.8 I. So please, we have to be very careful about this negative sign. Yeah. And here it's plus. Good. So the negative sign is on the 10.8. Good. That's nice. So we are almost done. Let's move to another one. Good. The total electric field of the point is the vector sum of the field due to all charges present. So as we said for the superposition principle of the electric force, it's the same for the electric field. If we have many points of charge at the point producing an electric field at the point P, the total electric field at the point P must be the sum of these individual fields. And we can write the electric field is KE, the sum of QI RI squared multiplied by unit vector. Okay, this is very good example. Example 21.8, point charge Q1 equal 12 nanocoulomb and Q2 equal negative 12 nanocoulomb are placed 10 centimeters apart. Compute the electric field caused by the charge Q1, the electric field caused by the charge Q2, and the total electric field at the point A, then at the point B, and then at the point C. This is our figure. Let's start by the first situation. The electric field at the point A, and of course, E, let's say at the point A. What do we have? We have a positive charge, negative charge. This is Q1, this is Q2, and there is a point between them, call it A. Okay? So let's come back to the figure. The distance from Q1 to A is 6 centimeters. The distance from Q1 to A is 6 centimeters. The distance from Q2 to A is 4 centimeters. Good. Good. Now, the electric field produced by Q1 on the point A is outward or inward? Good. It should be outward because the charge is positive. So this is E1 on A. And where is it? E2 on A. It's inward. Why? Because the charge is negative. So this is E2 on A. Where is the vector sum? Where is the total vector? Is the vector sum. So E at the point A, it should be E1 at the point A plus E2 at the point A. All of them along X. So no need to go through the component along X and along Y because the three vectors, E1A, E2A, and EA, all of them along X. Okay, so our question is come back to this quantity, termination of the quantities. E1A. E1A, as the definition, it's K Q1 over R1 to A squared multiplied by the R1 to A, the unit vector of 1. Okay, so it will be 9 times 10 power 9 times Q1, how much? He said Q1, it's 12 nanocoulomb. 12 times 10 negative 9 divided by the distance between the Q1 and A, it's 6 centimeters, so that means 0.06 squared multiplied by the unit vector. The unit vector of the x-axis is I multiplied by the vector I. What is the unit vector produced by the unit vector for the for the charge Q1? Q1 is R1A is from the point to from the charge to the point. So this is R1A hat. So as you see here, it's along the positive x-axis, so it's a unit vector I. Okay. So this is good. So let's go through the calculation. So it should be equal to 9 times 10 power 9, 9 times 10 power 9, multiplied by 12 times 10 power negative 9. So we can cancel this 10 power 9 on negative 9, divided by 0.06 squared. Good, 0.06 squared. So the result is 30,000. That means 3 times 10 power 4, 30,000 Newton per Coulomb along I. Good. Very good. So this is the first vector. Let's move to the second vector. Using the same way, E to A, it should be K Q2 over R2 to A squared multiplied by R hat to A. Okay. Should we put the absolute value? No, we don't put the absolute value. 9 times 10 power 9 multiplied by negative 12. In this case, Q2 is negative 12 times 10 power negative 9, because it's nano-Coulomb, divided by the distance between the point charge to the point field. It's 4 centimeters, so that means 0.04 squared multiplied by R hat to A. R hat to A is a vector pointing from the charge Q2 to the point A. So this is our vector, R hat to A. Good. So is it a long x or a long negative x? It's a long negative x. And since we are talking about the x-axis, so the unit vector is minus I in this case. Good. So did you understand from where it's coming, this negative sign? It's coming because the unit vector of the field points toward the negative x, not toward the positive x. So here you see that we have negative sign. They will cancel each other because we have multiplication. So the total electric field, the electric field at the point Q at the point A produced by the point charge 2 should be pointing to the positive direction, as we see in this figure. Good. So what will be the result? So let's calculate again. So it's divided by not 0.6, it's 0.4. And then it's 12. Negative, negative, they will cancel each other. So the result is 67,500. 67,500 I, and the unit is Newton per Coulomb. Now, what is our electric field at the point A? It's the vector sum. So it's 30,000 I plus 67,500 I. So it's equal 9,7,500 I Newton per Coulomb. Very good. So this is our electric field at the point A. Any question? No questions. Let's move to the point B. According to the question, he said, calculate the electric field at the point B. Where is the point B? The point B is located far from Q1 by 4 centimeters, but in this case, to the negative direction. As usual, let's draw the situation. At the point B, what do we have? We have Q1 and we have Q2 and we have Q2 negative. The distance between Q1 and Q2 is 10 centimeters, because we have 6 centimeters plus 4 centimeters. And the point B is here. It's far from Q1 by 4 centimeters. Now let's draw the electric field produced by Q1. Q1 is positive, so the electric field is outward. This is E1B. Now we are talking about the point B. What is the electric field produced by Q2? Q2 is negative, so the electric field is inward. That means it's directed to the positive X. To B. Very good. What is our positive direction? So this is positive. As usual, and as we did before, the electric field at the point B should be the sum of the two electric fields. E at the point B, it should be E1B plus E2, E2B. So, like the previous case, the two vectors have the same. They are located along the x-axis, whatever it's positive or negative. So no need to go through the component x and y. So now just along x. So as I said, no need to go through the y component. Okay. Now our question comes back to the determination of this quantity, as we did before. E1b, according to the definition, it's K Q1 over R1b squared, multiplied by the unit vector R hat between from 1 to B. What is R hat? For the first charge, pointing is the vector, is the unit vector pointing from the point charge to the point field. So this is 1B. And what is this? It's R2B. Good. خلاص. Just we substitute by the numbers. So it's 9 times 10 power 9 multiplied by 12 times 10 power negative 9 divided by the distance from Q1 to B. It's 4 centimeters. That means 0.04 squared multiplied by the unit vector R1 and R1B. R1B, it's toward the negative x. So we write here minus I, not I, because the unit vector pointing toward the negative x. Good. So this quantity will be 67500 I. Don't forget that there is a negative sign. Newton per coulomb. Good. Now let's come back to the second vector, E2B. E2B, it should be also K Q2 divided by distance from 2 to B squared multiplied by the unit vector R2B. So it will be 9 times 10 power 9 multiplied by Q2, it's negative 12 times 10 power negative 9 divided by the distance from Q2 to the point B, which is equal 14 centimeters. That means 0.14 meter, and it's squared. The unit vector of the electric field E2B is also directed to the left from the charge to the point. So we write minus I, the same. And we compute the electric field produced by the second point of charge. So let's write here 9 times 10 power 9 multiplied by 12. Okay, we will add the negative sign times 10 power negative 12, negative 9 divided by 0.14 squared. So our result is 5,510. 5,510 Newton per coulomb. Is it a long I or negative I? We have negative sign, so it's only longer I Newton. Let's do a short verification, a quick verification. A quick verification gives E2B is directed toward the positive x, E1B toward the negative x. For that, we have negative sign. Here we have plus. What is our total vector EB? It's the vector sum. So it should be negative 67500I plus 5510I. So what's going to be the result? Okay, so it's 67,500. No, it's minus 67,500 plus 5,510. So our result would be minus 61,000 and 61,990. 90 I. In two significant figures, it will be 62 with a negative sign, 0. Hi. Good. Newton per Coulomb. Class, we are done with this example. Now let's move to the second one, to the third one. At the point C now. At the point C, what is the point C? What is it? Yeah. At the point C, at the point C, what do we have at the point C? At first, let's draw as usual. We said that this is our positive and this is our negative charge. This is Q1 and this is Q2. And what is our point of charge? What is our point C? Point C, it's here. This is our point C. Okay, this point charge produces an electric field outward because it's positive. So this is AE1C, and it produces an electric field inward toward the charge Q2, E2C. Good. What is our total electric field? The total electric field is the vector sum. We draw the parallelogram formed by these two vectors, and this is E at the point C. Okay, good. So this is the x-axis, and this is the y-axis. Now we have components. Now we have components. Good. As we know, this distance is 10 centimeter. This distance, he said, it's 13 centimeter. 13 centimeter. And the same for here. It's also 13 centimeter. Good. Good, 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 good. Okay. Let's try to do it. At the point C, what do we have? E at the point C, the total electric field at the point C is the sum of E1C plus E2C. And as we said, we have components now. We have components. So we will take the x-axis along x. It will be EC as vector along x component. So it will be E1C along x plus the x component of E2C. Good. That's very nice. Okay, now the question, come back. What is this quantity? And we will repeat we should repeat the same steps for the y. Let's start by the first one. E1, E1C. The x component of E1C, according to the definition that we talked about it in the last lecture, we said it's the magnitude of E1C multiplied by cosine, what he said here, the angle. He said it's alpha, multiplied by cosine alpha. Cosine alpha. What is alpha? Is the vector between E1C and the x-axis. This is alpha. Let's say this is alpha 1. Let's say this is alpha 1. Multiplied by the unit vector of the x-axis I. Okay, from where we got this quantity E1, magnitude of E1C, it's from the formula. So it will be K, absolute value now of Q1 divided by the distance from 1 to C squared. What is the unit vector? We said that the magnitude of the unit vector is 1. So no need to write the magnitude of the unit vector. Okay, multiplied by cosine alpha 1. You see here, what is alpha 1? Alpha 1 is where? According to the figure here, alpha 1 is the same here. How to do that? How to explain that? This is alpha 1. The same alpha 1 here, it's the same format. So cosine alpha, as you know, it's the opposite, is the adjacent divided by the hypotenuse. But to apply cosine sine, we must have right angle triangle. So where is our right angle triangle? This is right. Yeah, this is our right angle. So what must be the adjacent in this case? The adjacent should be 0.05 meter. Okay, should be 5 centimeter. Let's write it's 5 centimeter, not 10 centimeter, because we are talking about right angle triangle. So it's multiplied by the adjacent, which is 5. So let's write here it's adjacent divided by hypotenuse multiplied by our unit vector. Good. So what will be? It will be 9 times 10 power 9 times Q1, absolute value of Q1 is 12 times 10 power negative 9 divided by the distance from Q1 to the point C, it's 13 centimeters, so it's 0.13 squared. Multiplied by the adjacent is 0.05 divided by the hypotenuse is 13 centimeters, that means 0.13. And it's a long I because we are talking x-axis. Okay? So what will be the result? Let's try to do it. So we said it's 9 times 10 power 9 multiplied by 12 times 10 power negative 9 divided by 0.13 squared multiplied by adjacent over hypotenuse, that means 0.05 divided by 0.13, yes. So it's a okay, 2,460, 2,460 if we take three significant figure. Or let's write in 4 significant figures, so it would be 58. Let's write in 3 significant figure, 58. 58 I Newton per Coulomb. This is our first vector E1C. We will repeat the same E1C elongates. Yeah, we will repeat the same steps, but for E2C. For E2C along X, that means the X component. So it will be E2C in magnitude multiplied by cosine alpha 2 now multiplied by the vector I. Alpha 2, where is it? This is alpha 2. Alpha 2, we said, this is very important to understand. So alpha 2 with respect to positive X to apply the sine and the cosine for the X component cosine and for the Y component sine. Where is our alpha 2? I will draw with another color. No, let's take orange, for example. And this is our alpha 2. Yeah, this is alpha 2, the direction of the second vector. But in the figure here, he said that it's the same, we have the same alpha here, the same alpha. Yeah. So he said that alpha 1 also here. What is the relationship between alpha 1 and alpha 2? The relationship between alpha 1 and alpha 2 is the following. Alpha 2 is 360 minus alpha 1. Yeah. Okay. Let's continue. Cosine 360 minus alpha 1. It's equal to cosine alpha 1. So we come back to the same cosine. Okay, we are coming back to the same cosine. Cosine alpha 1 is equal to cosine alpha 2. This quantity is cosine alpha 2 equal to cosine alpha 1. And which is equal We said it's 0.05 divided by 0.13. Why we did all of this? Because we are talking about another vector with an angle alpha 2. And alpha 2 is 360 minus alpha. Okay, let's go through the calculation. So so it would be 9 times 10 power 9 times negative 12 times 10 power negative 9 divided by the distance. It's the same 0.13 squared. But here, don't forget that it's absolute value multiplied by 0.05 divided by 0.313. So we will got the same result and the same magnitude for the x component of the second vector. So it will be how much we said here, 2,458. Let's take two significant. Let's take three significant, 60. 2,460. 2,460 I Newton per Coulomb. Now, what is our total electric field? The total electric field log x, that means ECx, the x component, is 2,460 I for the first vector plus 2,460 I for the second vector. It would be 2,460 times 2. So it would be 4,920. 4,920 I. Good. So this is ECx. What about now the y component of the vector? You see here in this figure that, which is another color, okay. For the first vector, the y component is upward. For the second vector, the y component is downward. The same distance here, 13 centimeter, 13 centimeter. The same magnitude of charge, 12 nanocoulomb, 12 nanocoulomb. So the y component, okay, good. 1 second. Okay, for the y component, what do we have? ECy equal EC1y plus EC2y. However, EC1y, the y component of the first vector, and the y component of the second vector are equal in magnitude, but opposite in direction. But opposite in direction. So as a result, EC equals 0, log-wise, sorry. So what will be the result of EC itself, which is equal ECx plus ECy? It will be 4,920. What we said? Yeah, 4,920 I Newton per Coulomb. In which direction? It's along x only. Very good. So we are done with this example. Any question about this example? No questions. Now let's move. Now we will discuss this situation. A charge Q1, 7 microcoulombs, is located at the origin, and there is a second charge Q2, minus 5 microcoulomb, is located on the x-axis 0.3 meter from the origin. Find the resultant electric field at point P. The coordinates of the P is 0 log x and 0.4 log y. Okay, very good. Just withdraw the situation as usual, because I want to go through the steps. So we have Q1 is here, Q2 is here, and the P is at this position, log y, 0 and 4. Okay, So the electric field produced by Q1 at the point P is outward. This is E1P. Good. The electric field produced by E2 at the point P is inward because it's negative. E2 at the point P. Very good. Very good. The distance between the two charges, he said, 0.3 meter. The distance from Q2 to the point, it's 0.5 meter. The distance from the charge Q1 to P is 0.4 meter. The question is, what is the total electric field at the point P? According to the superposition principle, it's E1P plus E2P. Very good. Very good. Where is our X and Y axes? The X axis is here. The Y axis is upward. We see that for the first vector, we have only Y component. For the second vector, we have two components. Two components. Let's start by the first vector, by the X component. Along X, EP along X is equal E1X plus E2X. What about the X component of the first vector? There is no X component of 0. Plus the X component of the second vector, it's K, Q2 divided by the distance between 2 and P squared in absolute value multiplied by cosine alpha multiplied by the unit vector I of the X axis. What is our alpha? Our alpha must be with respect to the X axis. So this is, let's say this is alpha 2 for the second vector, alpha 2. What is, okay, alpha 2, as we said before, cosine, let's say this is alpha 1. Let's say this is alpha 1. Let's say that this is alpha 1. According to the figure, alpha 1, it's here, also here. Alpha 1, it's also here. What do we said about the cosine? Cosine 360 minus alpha 1 is equal to cosine alpha 1. And alpha 1 is what? Cosine alpha 1 is 0, the adjacent divided by the hypotenuse. 0.3 divided by 0 by 0.5. 0.3 divided by 0.5. Good. Us now will just be substituted by the numbers. So EX, it will be K 9 times 10 power 9 times Q2. How much? Q2 is minus 5 microcoulomb. Minus 5 times 10 power negative 6, all of them in absolute value, and divided by the distance squared. The distance is 0.5 squared. Multiplied by cosine alpha. Cosine alpha is 0.3 divided by 0.5. Multiplied by the unit vector. And let's try to calculate. So we said it's K times 10 power 9. Multiplied by 5 times 10 power negative 6. Divided by 0.5 squared. And all of them multiplied by the cosine, which is equal 0.3 divided by 0, divided by 0.5. So the result is 10.8 times 10 power 5. Okay, so it's EX equal 10.8 times 10 power 3, 4. 10 power 4 Newton per Coulomb. So this is our first vector, our first component. Now let's discuss the second component of this vector. Good. For the second component of this vector, we said it's E2 ECY. It's E1CY plus E2CY. For the first vector, The first vector, E1C, it's a long y. So no need to write the sine and cosine. So E1C. So let's write directly. It will be E1CY, it will be KQ. So that means 9 times 10 power 9. Q1, how much Q1? Q1, we said it's 7 microcoulomb. 7 microcoulomb, 7 times 10 power -6, divided by the distance from Q1 to P, it's 0.4, 0.4 squared. And it's a long y, that means J. Okay? Why we don't write sine and cosine? Because this vector is a long y. The direction is 90 degrees. Sine 90 is 1. So we need to plus K, 9 times 10 power 9, Q. How much is Q? We will repeat the same steps. So it would be what we said here. So -5 times 10 power -6 absolute value divided by the distance. How much is the distance? 0.5. 0.5 squared multiplied by sine. Okay, multiplied by sine. They are alpha 2. Okay, multiplied by the vector j. But sine alpha 2 is equal 360 minus alpha 1. Sine 360 minus alpha 1 is equal minus sine alpha 1. It's okay? And sine alpha 1, how much? Sine alpha 1, it will be the opposite. What is our opposite? The opposite is 0.5 divided by the hypotenuse, which is 0.6, 0.5, 0.04 divided by 0. Did you understand from where this negative sign is coming? So, and we see that the vector, the y component of this vector, the y component of the vector 2 is directed downward. So we should write a negative sign. But from where it's coming, the negative sign, it's from the direction of the vector. Okay. So let's write here. Okay, so sine alpha 2 will be negative. We will substitute the sine. Okay, we will substitute the sine of alpha 2 by minus 0.4 over 0.5, opposite divided by hypotenuse. So what will be the result? Okay, 9 times 10 power 9 multiplied by 7 times 10 power -6 multiplied by divided by 0.4 squared. So it's 40 times 10 power 4. 40 times 10 power 4 J plus okay, instead of 5 or 7 of 5 we will write 4, we will write 5. Instead of 7 we will write 5, and we will multiply by multiplied by 0.4 over 0.5 with a negative sign. So the result 14.4 times 10 power 4 J. And don't forget that there is a negative sign coming from this side. Okay, so what will be the result? So our result will be 40 minus 14.4. So it's equal 25.6. So it's 25.6 times 10 power 4 J. Good. So this is E, C longer Y. Now, what is our total vector? EC. It's ECX plus ECY. So it's not C, it's P. Okay, whatever. So what will be? How much is the X component? The X component 10.8. 10.8 times 10 power 4I plus 25.6 times 10.4J. And this is our vector. Is it okay? Okay, so now we got the vector at the point C or at the point P. Now let's try to calculate its magnitude. The magnitude of the vector is square root of 1.08, 10.08, 10.8 times 10.4, this is squared, plus 25.6 times 10 power 4, and this is also squared. So it's equal square root of 10.8 squared plus, plus 25.6 squared. It's equal 27.8. 27.8 times 10 power 4 Newton per Coulomb. This is the magnitude. What about the direction? Tan inverse, let's say it's phi. According to the question, he said it's phi, according to the figure. Tan inverse of the y component. The y component is 25.6 divided by 10.8. Both of them 10 power 4, 10 power 4, they will cancel each other. So let's write 10 power 4. So they will cancel each other. So our result will be tan inverse of 25.6 divided by 10.8. So it's 67.1. 67.1 degrees. Should we convert this angle? Should we add something 180, 360? No, because our total vector is along the y in the first quadrant. So this is our vector is in the first quadrant. Very good. Very good. So we are done with this example. Now just we have one more question. Find the electric force exerted on a charge of 2 times 10 power minus 8 Coulomb located at P. If we come to the point P and we add a charge, this charge equal to 2 times 10 power minus 8 Coulomb, what will be the total electric force exerted on that charge? As we know, the force is Q multiplied by E. If we apply the formula, so that means just we write the vector E or the magnitude of E1 multiplied by the charge. Okay, so خلاص we are done with this part. Now let's move to the motion of particle in uniform electric field. I would like to explain here, and I would like to say that if we have a point of charge between two parallel plates, one is positive, the second one is negative, the charge is positive, so the charge will move toward the negative, will be derived toward the negative plate. Okay. If we want to apply Newton's law, how many force we have? Since we have an electric field and we have two parallel plates, one positive, one negative, so we have an electric force, right? So this point of charge will be submitted to the influence of electric force, and there is a gravitational force also. But what do we say about the gravitational force? It's neglected. We will neglect this. So according to Newton's law, the sum of the force is equal MA, the sum of the forces equal MA. How many force we have? We have only electric force. The electric force is QE. So that means QE equal MA. By arranging this equation, so we get the acceleration equal QE over M. And this is the acceleration of the point of charge between the two parameters. The acceleration of a particle of the particle motion is constant as far as E is uniform. We say the word uniform for the vector, and we say the word constant for the scalar. In uniform electric field, A is uniform also. So that means all kinematic equations are fine. So what are these kinematic equations? The kinematic equations are the following. From the physics 1, when A is constant, we can write x final equal x initial plus v initial xt plus half of ax t squared. This is for the position. For the velocity, v along x is v initial x plus ax t. The third equation is without time, so vx squared equal v initial x squared plus 2ax delta x, that means x final minus x initial. The last equation, delta x, x final minus x initial, equal v initial plus v final over 2, let's say along x, multiplied by t. This is the average velocity. Okay, so these are the kinematic equations when we have a constant acceleration. Good. We take an example. Before the example, the direction of the acceleration should depend on the sign of q. As we said here, A equal QE over M. When Q is positive, A and E in the same direction. When Q is negative, A and E are opposite in the direction. Positive. Okay, we take an example. A positive point charge Q of a mass M is released from rest in uniform electric field E directed along the x-axis. Describe its motion. Gives equations for displacement, velocity, acceleration, and kinetic energy. Good. So this is how we would describe the motion. Okay. It's the same example, but we will treat this example. An electron of charge minus E is projected horizontally into a uniform electric field in the direction of positive y direction. Describe the motion. Describe the motion, that means write the equation of y as a function of x. Okay, so what we're going to do in this case? In this case, we will do the following. What is it? We will take the figure with the initial conditions, and we will try to solve. As you see here, the electric field is uniform. E is uniform. Uniform, because we have parallel plates. So that means the acceleration is constant. Okay, that means kinematic equation. Good equations. Good. The electric field is okay. He said in the question, an electron. Electron means Q is negative. That means our acceleration is opposite to E. Our acceleration in the opposite direction of E, because we are talking about electrons. E is upward. That means A is downward. Good. Let's write the equations of motion. Upward means we have y. We don't have x. So that means we will write the equation of y. Let's start by x. X is x initial plus v initial xt plus the half of ax t squared. Good. Just be substituted by the numbers. X initial, we start from the 0. So it's 0. The initial velocity, v initial x equal vi. V initial y equals 0 because the electron is projected horizontally. So we write here vi t plus the acceleration downward. So that means the acceleration log x is 0. Okay, that means our acceleration log x is 0. What about our acceleration log y? Our acceleration log y, it will be minus e, which is q, multiplied by e divided by the mass of it. So that's all. This is what we have. Let's write here plus 0 to understand. So that means x final equal v initial t only. Let's talk about the y. Y equal y initial plus v initial y t plus half of ay t squared. So it will be the y initial, we said also it's 0, plus v initial log y, it's also 0, plus the half of the acceleration minus e electric field divided by the mass of proton of the electron multiplied by time squared. So this is our equation log y. What do we have in common between x and y? We have the time. So the time here is equal x final divided by v initial. So we can write this equation as y equal, let's take another slide, it's better. Y equal half of minus e over m multiplied by t squared will be minus 1 over 2 e over m multiplied by x over v initial squared. And we can write y equal y final equal minus e over m over 2m v initial squared multiplied by x squared. This is the equation, can be written as a form of constant multiplied by x squared, which is the equation of a parabola. Okay, so the trajectory of our particle is a parabola, and we are done with this example. Hence, the trajectory is parabola. We take this example, and we will be done with this lecture also. Okay. When the terminals of the battery are connected to two parallel conducting plates with a small gap between them, the resultant charges on the plate produce a nearly uniform electric field E between the plates. In the context section, we will see why this is. If the plates are 1 centimeter apart and are connected to 100 volt battery, as shown in the figure below, the field is vertically upward and has a magnitude 10 power 4 Newton per Coulomb. Question 1, question A, if an electron is released from rest at the upper plate, what is the acceleration? Now, we have two parallel plates. An electron is released from rest from the upper plate toward the lower plate. We took the positive direction toward the negative, the positive plate in the direction of motion of the electron. In this case, what we're going to do is asking about what is the acceleration of the electron. Question A, the acceleration of the electron as the electric field is uniform equal QE over M. Q is minus E. The electric field is 10 power 4, minus E is 1.6. times 10 power negative 19 times 10 power 4 over the mass of the electron. He said it's 9.11 times 10 power negative 31. Okay, in which direction? Is it along y or along negative y? It's with the y. The electron is moving with the y, downward. So let's write J, and we write here downward. Very good. So we got the acceleration equal 1.6 times 10 to the power negative 19 times 10 to the power 4 divided by 9.11 times 10 to the power negative 31. So the result will be 1.7576 times 10 power 14. 15 J. And don't forget that we have okay. There is something missing. We missed something. We missed a step. The electric field E is upward. The acceleration is downward. The positive direction is downward. So the electric field must be minus. Minus, okay? Good. So it will be plus here. No need to write plus or minus, so directly this. This is our acceleration. With the magnitude equal 1.76 times 10 power 15. Meter per second squared. Very nice. Okay. Question B, what he said in question B. What is the speed and the kinetic energy does it acquire while traveling 1 centimeter to the lower plate? So imagine that our electron is traveling for 1 centimeter from the upper plate to the lower plate. Did we have any information about time? No. So we use the third equation. V squared along y equal V initial squared along y plus 2ay delta y. Okay, just we substitute by the numbers and we got the result. Vy squared equal V initial. Initially we start from rest. Plus 2 ay how much? Ay we said it's 1 point times 1.76 the y component, multiply times 10 power 15 multiplied y final. We start from the 0 and we travel 1 centimeter downward with the positive direction. So it's y final 0.01, 1 centimeter minus 0. So we need Vy, not V squared. So we apply the square root. Okay. So what will be Vy at the lowest lower plate? It will be the square root of 2 times square root of 2 times 1.76 times 10 power 15 multiplied by 0.01, 1 centimeter. So the result will be times 10 power 6. So our result will be 5.9 times 10 power 6 meter per second. Yeah, it's very high speed because we're talking about accelerated electron. Last question, he said, no, before. What is the kinetic energy? Kinetic energy Kinetic energy, it's half of mv squared. So it's half the mass electron 9.11 times 10 power negative 31 multiplied by 5.9 times 10 power 6 squared. So what will be? 0.5 multiplied 9.11 times 10 power negative 31 multiplied 5.9 times, okay, before there is a bracket, times 10 power 6, and this is squared. The result. So it's 3.76 times 10 power negative 16. So 3.76 times 10 power negative, what is it? Negative 16 joule. The last question of this lesson, of this example, how does it long to travel to the lower plate? Question C is asking about the time. We have V long y equal V initial long y plus AY T. So this is equal V final. How much we said V final? It's 5.9 times 10 to the power 6. 10 to the power 6 equal the initial is 0. Acceleration, our acceleration 1.76. 76 times 10 power 15 multiplied by the time. We are asking about the time. So our time will be 5.9 times 10 power 6 divided by 1.76 times 10 power 15. So the result is 5.6 divided by 1.76. So it's 3.18 times 10 power negative 9 seconds. Okay, so we are done with this example. Let's see if we have other questions. Halas, we are done. Thank you so much and see you in the next lecture.